Advanced Math Lesson 91, Geometric Progressions. Geometric progressions are very, very similar to arithmetic progressions or arithmetic sequences. The difference is that in geometric progressions we're going to be using multiplication as opposed to the arithmetic sequence where we're just adding. If you want a little idea as to why this one's called geometric as opposed to arithmetic, if you think about multiplying that puts you into the second dimension, or area could also be another expression of multiplication. So it's a much more geometric process, as it can also represent areas and volumes in multiple dimensions. Anyways, that's not the point of this lesson. The point of this lesson is how in the world do we solve geometric progressions. If you need to review arithmetic sequence, that's back on lesson 87. You can go back and look at that now. But we really don't need to look at that too much. You could learn each one of these individually without knowledge of the other. So without further ado, let's talk about geometric progressions. So geometric progressions are simply, if we start off with a number, let's start off with 4. And then we just take the number 4 and we keep multiplying it by, fix my focus. Okay, and then let's just multiply it by 3. All right. So if we take 4 times 3, that would then give me 12. And then we multiply that times 3, and then that would give me 36, and then that times 3 would give me a bigger number. Let's see here, 108. Right, and then that would be the geometric sequence. In this sequence, 4 would be term 1. So, or what they use A, don't they? Let me double check in this book. Yeah, this book uses the notation A. So 4 would be A sub 1, 12 would be A sub 2, 36 would be A sub 3. 108 would be A sub 4. So that's our geometric progression. I feel like my camera keeps going in and out of focus. This is weird. That's much better. Okay. Now the question is, how do we find different terms in a sequence, or what formula necessarily we're going to use to solve for missing terms in a sequence? And then the other thing we have to talk about is the common ratio. Forgot about that. So in this, the multiplication of 3 is what we call the common ratio. In arithmetic sequences, we called it the common difference. This time we're calling it the common ratio. The reason why is because of inverse operations. In addition, the inverse operation is to subtract, and the answer to that would be a difference, or the common difference between each number. In multiplication, the opposite action would be to divide. And then divisions are also similar expressions as fractions, and ratios being the another way of representing a fraction or a division. So that's where the term common ratio comes from, and that's what we use to express this number 3. So for example, this sequence I've laid out right now, this would be a geometric sequence whose first term is 4, and the common ratio, or I'm just going to put the ratio, would be 3, right? And then 108 would be the 4th term in a geometric sequence whose first term was 4 and whose common ratio is 3. So let's use this knowledge really quick to answer one of our practice problems. We're told to find the 5th term. So find the 5th term in a geometric sequence whose first term, so the first, is equal to -2. And the common ratio, excuse me, and the common ratio is equal to -3. So what we're going to do is, if we'll take this really basically, we'll just make a map of it. We'll have A sub 1, A sub 2, A sub 3, A sub 4, A sub 5, right? So our first term we know is going to be -2, and then between each of these we're going to have to multiply by -3, -3, -3, -3. So what you see here is, in order to get from the first term to the 5th term, we're going to have to multiply by -3 1, 2, 3, 4 times. So whatever term you're looking for, you take your common ratio and you raise that to the exponent of that term minus 1. So the fast way to solve this using the equation is we would take A sub 1 times R to the power of whatever term you're at, A sub n minus 1. So to fill this in, a sub 1 is negative 2, r is negative 3, your common ratio, and then the exponent would be fifth term minus 1, or 5 minus 1, which would be 4. Excuse me. I think I need to drink some water. Okay. All right. So then we just take negative 3 to the power of 4. Since it's a positive since it's an even exponent, we know that all of our negatives are going to cancel. So this is going to end up being pretty much the same as 3 to the power of 4, which is, hold on. I didn't pull my calculator out this morning. Let me see if I can do this in my head. 3 times 3 is 9, times 3 is 27, times 3 is 81. Yep, 81. So negative 3 to the power 4 is equal to 81. So now what I have is negative 2 times 81. That gives me negative 162. So the fifth term is going to be negative 162. And let's check if that's correct. Yep, we did it right. Okay, so again, this is the key thing we want to remember right here. You take the first term, multiply it by the ratio raised to the exponent of whatever term you're looking for, minus 1. So let's see if we can take this equation and apply it to a different type of scenario. For example, let's see here. One problem tells us to find 3 geometric means between negative 16 and negative 1. So we have to do a little bit more counting here. So if we're finding 3 numbers in between these, then that means negative 16 is a sub 1, and then the 3 numbers would be a sub 2, a sub 3, a sub 4, which means that negative 1 is a sub 5. So if we have to find the 3 geometric means between them, we're going to use this equation that we have up here, except instead of solving for a sub n, or figuring out what this answer is equal to, we'll be setting this equal to negative 1. So if I fill in the blanks here, a sub 1 is going to be negative 16. The ratio is going to be unknown. The exponent we know is going to be 4 because we're looking for a sub 5, and that is going to equal the value of a sub 5, which is negative 1. So using all this information, all I have to do now is solve for r. So I can go ahead and divide each side by negative 16. That becomes positive. So now I know that r to the power of 4 is equal to 1 over 16. We can use some exponents, or we could we could just take the 4th root of each side, because I know that the 4th root of 16 is 2. So let's see here. That's going to give me 1/2. Wow, my brain's working a little slow. And then the 4th root of r sub 4 is going to be r. So r is going to equal 1/2, but remember, because of me taking the 4th root, I have to add a plus or minus sign there. All right, so this is going to be positive or negative 1/2. So if the sequence is, or if the ratio is positive or negative 1/2, then to find the 3 terms in between, then I have to take negative 16 and multiply it by positive 1/2 or negative 1/2 3 times. So 16 multiplied by positive, or negative 16 multiplied by positive 1/2 will give me negative 8. That multiplied by positive 1/2 would give me negative 4, and then that multiplied by positive 1/2 would give me negative 2. So that's one option. The other option is if I use negative 1/2 and then I take negative 16. Whoops, I just realized that was off camera. So if I take negative 16 times negative 1/2, I'll go ahead and write this out so we don't get confused. This would actually become positive 8. Positive 8 multiplied by negative 1/2 would become negative 4. Negative multiplied by negative would give me positive 2. So these are our 2 options. And you'll notice that when you're looking for geometric means, you're going to have 2 sets of answers. Let me reread this. Find 2 geometric means. Okay. It seems like it'd be okay. I don't see anything in the book saying that you have to show both sets of answers. I think it would be a good habit, so that way we're not forgetting about our plus or minus nature of roots, 4th roots, cubed roots, etc. But that's how we use this equation right here. That's how we do geometric sequences. If you have any questions, let me know on the school website, and I'll see you in class.